Hello everybody. Okay, now in these videos what I'm going to do, I'm going to go over every problem that I will set, well not every problem but most of the problems I think that you might have trouble with, and in the beginning, at the beginning of our electricity unit, I'll go through certainly most of the problems, so you've got some resource to go through or go to check your understanding. And so in this video, I'm going to go through the questions that I've set in chapter 4.1. And we're going to start with question 1. So here we go. Now in this question, you'll notice that there's a circuit drawn. And each of these objects here, A, B, and C, are globes. Now if we look at the question, it states that the lobes are identical. Okay, so each of those globes is the same. Now what that means to us is that the resistance they're going to offer will be the same. So the resistance of this globe will be the same as B and C. So they are identical globes. The other thing you need to note in this problem is that there is a switch. This is a switch. And when the switch is open, no current can pass through that part of the circuit. When the switch is closed and that lever is connected, then current can flow through. So if we look at the question, it's asking us, so when the switch is closed, what will happen to each of the following? Intensity of lamp A, intensity of lamp C, current in the circuit, and so on. So what it's asking us to do is to work out what will happen with each of these. Now notice there's no numbers, there's no calculations involved here other than possibly a little bit of basic algebra. So the other thing we need to be aware of that here is our battery, and sometimes a battery is defined as E, which stands for the electromotive force, which basically you don't need to know what that means. All that means it's the source voltage of our circuit. Okay, so that's the voltage of our battery basically. So E, this little value here, that's the voltage of the battery. Okay, so let's have a go at this problem. Now, it's asking us when the switch is closed, what will happen to? Part A, what will happen to the intensity of lamp A? Now, intensity is telling us, it's asking us about how bright the light will be or how will its brightness change. So the intensity is related, the intensity of a light is related to the power. The power being consumed by that light globe. And power, if you remember, is the rate at which it actually converts electrical energy into heat and light. Power is measured in watts. Okay, power is measured in watts. And you may also remember from the previous videos that power equals VI. So we'll write that down over here. So P, power equals VI. Now the other rule that we will always use is Ohm's law, which is V equals IR. Now you might also remember that these two formulas, both of them have both a global version and a local version. Now if we're talking about the global version, we're talking about the entire circuit as a whole. If we're talking about the local version, we're talking about a particular component of the circuit. Okay, so let's have a look at this first question. If we close the switch, this switch here, then what's actually going to happen is that we will now connect that part of the circuit. So there's our closed switch. Now what does that mean? What's that going to do with our circuit here? What's going to happen? Well, previously, when that was open, all the current would have had to have gone right around that circuit. That's the way the current would have gone, because none of it would have been able to go through this middle branch because the switch was open, not allowing any current to go. Which meant that initially this circuit was a series circuit with 3 resistors in series. So that means, therefore, that once we close this switch, we've changed the path of the circuit, because now when the current comes out of the battery and passes through these first 2 globes, it reaches a junction. It can actually go through globe C or down this switch. Now, what actually will happen is that basically all of the current will go through the switch. Why? Because there is 0 resistance through this part of the circuit. 0 resistance. So if a current reaches a fork in the road, if you like, and one path or one fork or one branch has significant resistance and the other branch has no resistance, then virtually all of the current will pass through the branch with no resistance. So that effectively means 2 things. Firstly, it means that because no current is now passing through this part of the circuit, it's basically not functioning. So we can almost eliminate that now from the circuit. So now all the current is just going to pass through these 2 globes and back to the battery. So if all the current is now passing through only 2 globes and not 3, what is that going to do to the resistance of the circuit? Well, because there's now only 2 globes in our effective circuit, not 3, the resistance will be reduced. So the resistance will be reduced, the resistance of the whole circuit. And that also means that there will be more current. Now, why will there be more current? Well, the reason is because of Ohm's law. Let's have a look. This is Ohm's law, and we're going to look at the global version. If V equals IR, in other words, remember, for the global version, V is the voltage of the battery, I is the current coming out of the battery, and R is the total resistance of the circuit. If we rearrange this so that I equals V over R, if we've reduced R, if that value there has reduced because we've removed one of the resistors effectively by closing this switch, and the battery voltage remains the same, that means our current is going to go up. So that means that current will increase. The current will increase. So now, because the current is increasing, we look at our power formula. The current's going to increase. If we increase the current, that will increase the power of our globe. And because the power is increasing, therefore the intensity will increase. So in actual fact, by closing the switch, the intensity of globe A and globe B will increase. Okay, we're now going to continue with question 1. Now, the other parts of the question were, part B, what happens to the intensity of lamp C when this switch is closed? Well, remember, if we close that switch, we discussed this in the previous section, if we close this switch, then all of the current will flow down this branch because there's no resistance. Therefore, no current will flow through globe C and it will actually be turned off. So globe C won't even glow. So it's turned off because no current will pass through it. Part C, was a question relating to the current in the circuit. What happens to the current in our circuit when this switch is closed? Well, once again, we talked about this a little bit earlier. When this switch is closed, all the current will flow through this branch. None of it will pass through globe C. So now all the current is now passing in this circuit like this, which means that the current now only has to pass through 2 globes, not 3. That has the effect of reducing the resistance. That will reduce the resistance, the total resistance of the circuit. And because the total resistance is reduced, using our global version of Ohm's law, V equals IR, that implies that I, which will be equal to V over R, because the total resistance is reduced, the current will increase. So the current coming out of the battery increases. Okay, part D. What happened to the potential difference across lamp B? This lamp here. Now you'll notice what I've done here. I've placed a voltmeter across each of the globes. That is the symbol for a voltmeter. And remember, a voltmeter measures, that's a voltmeter, and it measures potential difference. Potential difference. It measures potential difference, which is measured in volts. Now, just to recap, if this was a 9-volt battery, that means that every packet of charge that comes out of the battery, remember a packet of charge is known as a coulomb, so each of those is a coulomb of charge, and remember there are a lot of charges, a lot of elementary charges or electrons in a coulomb. In fact, there's 6.25 times 10 to the power of 18. So in each of those little packets, there's a whole lot of electrons. But remember, if it's a 9-volt battery, then each coulomb receives 9 joules of energy. Okay, so that's pretty simple. So the voltage of the battery tells you how much energy it gives to each coulomb as it flows around the circuit. Now, the other rule of circuits is that as the coulombs travel around the circuit, they have to spend all their energy. So by the time they come back to the battery, they must be absolutely depleted of energy. In other words, they have 0 electrical potential energy. So each of these coulombs, if this is a 9-volt battery, would have to spend 9 joules of energy as it goes around the circuit. Now, initially, this part of the circuit, this branch, was open, and therefore all the current would have had to have gone through all 3 globes. So let me just change colour for a second. Okay, so in the initial situation, all the current would have come out of the battery, travelled through all 3 globes, and come back to the battery. Because there's no other option. None of the current could have travelled down this middle branch because the switch was open. Didn't allow current to pass through it. And that would therefore mean that because the charges coming out of the battery have to flow through each of these resistors or globes, then they have to spend their energy getting through each of these resistors. Think of them as a ride, and each of those rides cost money. Now, remember, the problem told us that each of these rides are identical. Each of these globes are identical. So they're going to charge the same amount of money to go on each of those rides. Put another way, as the coulombs travel around the circuit, they're going to lose the same amount of energy as they pass through each of these resistors. And because they're going to pass through 1, 2, 3 of them, then the voltage across each of those globes initially would have been 3 volts. So that means that the potential energy, the electrical potential energy of our coulombs at this position, they still have their 9 joules of energy. They would lose 3 joules as they pass through this globe, and so at this position here, they'll now have an electrical potential of 6 volts. And as they pass through this second globe, they would use another 6 joules of energy. Now they're down to, each coulomb is now down to 3 joules of energy, which means the potential there is 3 volts. And finally, as it passes through this final globe, when they get to the other side of that, the potential energy, electrical potential energy of every coulomb at that point in the circuit will be at 0. So the potential will be 0 volts. It'll be 0 all the way back to the battery. So that was the original situation. But then the switch was closed. So in other words, we now close the switch. Now remember what happens when we close that switch? That effectively disconnects this part of the circuit. So now effectively, the current is now just flowing through these 2 globes and then back to the battery. Let's finish our circuit there. Okay, so what does that mean for our voltages? Well, they'll still be connected to the same battery, so they're still getting the same amount of energy as they come out of the battery, but this time they only have to go through 2 globes, not 3, which means because the globes are still the same, they'll have to spend half of their energy going through this globe and the other half through this globe. So that means that the difference in energy here will be 4.5 volts. And likewise here. Remember, by the time they get through all of the resistors or globes and get back to the battery, they must be at 0. So by chopping off this part of the circuit, by closing this switch here, the voltage across globe B has actually increased, as has the voltage across globe A. They would have originally been, if it was a 9-volt battery, 3 volts each. Now they've increased to 4.5 volts, these 2. And part E, looking at the potential difference across lamp C, well, at lamp C, remember effectively by closing the switch, all of the current passes through here, and that means that the potential, by the time the currents or the coulombs get to this point here, they are at 0 volts. Of course, originally that would have been 0 volts over here. The difference in potential across this globe is 0 volts because no current's flowing through it. And that's not the only reason. The reason why it's 0 volts is because the electrical potential energy either side of that globe is the same. It's 0 volts on this side and it's 0 volts on that side. So therefore the difference is 0. The last part of the question, the total power dissipated in the circuit. Okay, we will actually discuss that in the final phase of this video. I'll just clear these calculations and we'll look at that in just a jiffy. Okay, this is actually the hardest part of question 1, and it involves using algebra. The question is, what happens to the total power dissipated in a circuit? Now, first we have to understand what's that asking. What it's actually asking is how much energy each second is being delivered from our battery to the globes. And another way of saying it would be what is the total amount of heat and light that is being generated by the circuit or the globes in the circuit. And what we're doing, we want to know, does it go up or does it go down if we close this switch? Now remember, when we close the switch, we're basically bypassing the third branch in the circuit, because all the current wants to just go through this closed part of the switch because there's no resistance. Okay, so what we want to do, we want to look at these two scenarios. This first scenario is the circuit while the switch is open, which means that all the current will pass through all three globes and then back to the battery. After the switch is closed, effectively all the current will just pass through those two globes and back to the battery. Now remember that because this is now passing only two globes, the resistance has reduced. So that's the way we're going to work this out. So we're going to start with the idea. If we want to look at the total power being dissipated or converted into heat and light in both of these circuits, we're going to use our power formula, which is P equals VI. And basically we're going to use the global version. And the global version means that the power is going to be the total power dissipated in the circuit, which is in fact what the question is asking. So that will be the power which is lost as heat and light or converted to heat and light in the entire circuit, across all of the globes in the circuit. V is the voltage of the battery, which in this case we're going to call it E. And I is the current through each of these, or through the circuit, coming out of the battery. So what we're going to do, we're going to come up with an expression for the power in this circuit, circuit 1, and we're going to come up with an expression for the power in circuit 2, using basic algebra and no numbers whatsoever. This is a skill, and probably one of the hardest skills you need to master in physics generally, being able to solve a problem or analyze a problem when we change a quantity without being provided with any numbers. So let's see how we go. So firstly, I'm going to come up with an expression for the power in circuit 1. Well, power, in this case, power will equal the voltage supplied by the battery, which we'll call E, times the current. Well, we don't know what the current is, but we do know this. And we'll do this as a sidebar. We know that using Ohm's law, V equals IR, and rearranging that, I equals V over R. Now, if we're looking at the global version, that means the current coming out of the battery will be the voltage of the battery, which is going to be E, divided by the total resistance. So the power is the voltage times the current, but we know the current, that the current is going to be the voltage of the battery divided by the total resistance of the circuit. The voltage of the battery is E, and the total resistance of this circuit, because you've got three resistors, which I've just called R, and remember all the same, so if this was say 10 ohms, and that was 10 ohms, and that was 10 ohms, then the total resistance would be 30 ohms. And so the total resistance here would be 3R. So it's E times 3, beg your pardon, not times, divided by, my apologies. It's going to be, I is going to be E over 3R. So if we substitute this expression into where we see the I, we've got an expression for the power. Power will equal E times E over 3R. And that equals 2E over 3R, or 2/3 of E over R. Okay, so that is our power. That is an expression for the power that is being delivered from this battery to all three globes in the circuit. Let's do the same calculation in this circuit. And I encourage you to see if you can do it on your own before watching the rest of this video, and then use the video to check your answer. Okay, so over here, and I'll change colour so it stands out a bit more. So over here, the power dissipated by this battery will still be the voltage of the battery times the current. But the current's going to be different in this one. Remember we said the current has increased. Now, at this stage, you can probably already see if we've increased the current, then the power is going to increase. But let's actually see by what ratio, by what value it's increasing by. So the expression for the current over here, but the current in this case, remember the current is the voltage of the battery divided by R, but in this case there's only 2 globes. So it's going to be E over 2R. So if I put both of those expressions together, like I did over here, by substituting this expression for I now know that the power is going to equal the voltage of the battery, which is E, times E over 2R, which equals, I beg your pardon, that's not 2E, that's E squared. My apologies. E times E is E squared over 2R. Okay, well, it's just E squared over 3R. This is going to be E squared over 2R. And notice here that the denominator is going to be lower here than here. This is a smaller denominator, which means the power on this side must be larger. So more power is dissipated on this side, in this scenario, than in this scenario. So the final conclusion we can draw is that by closing this switch here, the amount of power delivered to the globes and changed into heat and light is actually increased. Remember, power is the amount of energy which is being changed into heat and light every second. So it's measured in joules per second, which is equal to a watt. Okay, so apart from that little miscalculation that I performed, I really apologise for that. That might have stressed some of you out. I apologise. That is the conclusion of question 1. Thank you.